Welcome to the channel. Please consider subscribing. I produce videos daily, covering a wide variety of cloud topics with a focus on networking. Also, hit the bell icon to get notified of new videos. Today, we're analyzing a Google Cloud Networking exam question that tests your understanding of VPC peering with custom route import and export. This is a crucial feature that enables complex hybrid networking scenarios. The scenario describes two VPCs that are peered together, with VPC N2 having a VPN connection to an on-premises network. The key detail is in point 4. Routes have been imported and exported for both networks. This tells us that custom route exchange is enabled on the peering connections. The question asks, in the route table for VPC N1, what is the next hop for traffic to 10.10.0.0/16? This tests whether you understand how custom routes propagate across VPC peering when import and export is enabled. With custom route import and export enabled, VPC N2's VPN route to the on-premises network, 10.10.0.0/16, is shared with VPC N1. This is a powerful feature that allows you to create hub and spoke architectures where one VPC acts as a connectivity hub. The most critical detail in this question is that routes have been imported and exported for both networks. This is not the default behavior of VPC peering, and understanding this is key to answering correctly. By default, VPC peering only exchanges subnet routes. If VPC N1 has subnets 192.168.1.0/24 and 192.168.2.0/24, and VPC N2 has subnets 10.0.3.0/24 and 10.0.4.0/24, these are the only routes that would be exchanged by default. However, when you enable export custom routes on VPC N2's peering configuration and import custom routes on VPC N1's peering configuration, something powerful happens. VPC N2 will now share all its custom routes with VPC N1, including routes learned from Cloud VPN, Cloud Interconnect, or manually created static routes. In our scenario, VPC N2 has a VPN connection to the on-premises network 10.10.0.0/16. This creates a custom route in VPC N2's route table. With export enabled, this route is shared with VPC N1. When VPC N1 imports this route, it appears in VPC N1's route table with the peering connection as the next hop. This feature effectively allows VPC N1 to use VPC N2 as a transit VPC to reach the on-premises network, without needing its own VPN connection. This is a common pattern in enterprise architectures where you want to centralize external connectivity. Visualizing the network architecture. Let's visualize how the network is structured and how routes flow between the components. In our diagram, you can see VPC N1 on the left with its two subnets in the 192.168.x.x range, and VPC N2 in the middle with its subnets in the 10.0.x.x range. The VPCs are connected via bidirectional peering. The peering connection from VPC N1's perspective is named VPC N1 to VPC N2, and from VPC N2's perspective, it's VPC N2 to VPC N1. These names are important because they appear as next hops in the route tables. VPC N2 has a cloud VPN connection to the on-premises network 10.10.0.0/16. This VPN creates a route in VPC N2's route table where the destination is 10.10.0.0/16 and the next hop is the VPN tunnel. Now here's the magic. With custom route export enabled on VPC N2's peering configuration, this VPN route is shared with VPC N1. When VPC N1 imports this route, because import is enabled on its peering configuration, it creates an entry in VPC N1's route table. The imported route in VPC-N1's table shows the destination as 10.10.0.0/16, but the next hop is not the VPN tunnel, as VPC-N1 doesn't have direct access to it. Instead, the next hop is the peering connection, VPC-N1 to VPC-N2. This tells VPC-N1 to send traffic destined for the on-premises network to VPC-N2, which will then forward it through the VPN. Let's examine the route tables for both VPCs to understand exactly how traffic flows from VPC-N1 to the on-premises network. VPC-N2's route table contains its local subnet routes, 10.0.3.0/24 and 10.0.4.0/24. The imported routes from VPC-N1, 192.168.1.0/24 and 192.168.2.0/24, and crucially, the VPN route to 10.10.0.0/16. The VPN route shows the VPN tunnel as the next hop because VPC-N2 hosts the VPN gateway. VPC-N1's route table is where the answer to our question lies. It contains its local subnet routes, 192.168.1.0/24 and 192.168.2.0/24, and the imported subnet routes from VPC-N2, 10.0.3.0/24 and 10.0.4.0/24. But because custom route import is enabled, it also contains the VPN route to 10.10.0.0/16. The key difference is in the next hop. While VPC-N2's route shows VPN tunnel as the next hop for 10.10.0.0/16, VPC-N1's imported route shows VPC-N1 to VPC-N2 as the next hop. This makes perfect sense. VPC-N1 doesn't have direct access to the VPN tunnel, so it must send the traffic to VPC-N2 via the peering connection. This is transitive routing in action. The traffic path is from a virtual machine in VPC-N1 to the VPC-N1 to VPC-N2 peering, then to VPC-N2 to the VPN tunnel, and finally to the on-premises network. VPC-N1 knows it can reach 10.10.0.0/16 through VPC-N2, even though it doesn't know the specific details of how VPC-N2 will forward the traffic. Evaluating the answer options. Now let's evaluate each answer option to understand why VPC-N1 to VPC-N2 is the correct answer. Option 1. Internet Gateway. This would only be correct if VPC-N1 had no route to 10.10.0.0/16 and the traffic followed the default route. However, with custom route import enabled, VPC-N1 does have a specific route to this destination. Additionally, 10.10.0.0/16 is private IP space that cannot be routed over the public internet. Option 2. VPC-N1 to VPC-N2. This is the correct answer. When VPC-N1 imports the custom route from VPC-N2, the next hop is set to the peering connection. From VPC-N1's perspective, to reach any destination that exists in or is reachable through VPC-N2, the immediate next step is to send traffic over the peering connection. Option 3. VPC-N2 to VPC-N1. This is the peering connection name from VPC-N2's perspective. It would appear in VPC-N2's route table for traffic destined to VPC-N1's subnets. Since we're looking at VPC-N1's route table, this is the wrong direction. Option 4. VPN tunnel of 10.10.0.0/16. This would only appear in VPC-N2's route table, not VPC-N1's. VPC-N1 doesn't have direct access to the VPN tunnel. Through the import-export mechanism, VPC-N1 only knows that it can reach this destination via the peering connection, not the specific details of VPC N2's VPN. The answer demonstrates the abstraction that VPC peering provides. Each VPC maintains its own routing perspective while enabling complex multi-hop routing scenarios. To solidify our understanding, let's use an analogy. Think of VPCs as cities connected by highways, or peering connections, and the on-premises network as a small town that's only accessible via a local road, a VPN tunnel, from one of the cities. If you're in San Francisco, which is VPC N1, and want to reach a small town, the on-premises network, that's only accessible via a local road from Los Angeles, or VPC N2, what would your GPS tell you? It would say, take Interstate 5 south to Los Angeles. The interstate is your immediate next hop. Your GPS in San Francisco doesn't need to know about the specific local road in Los Angeles. It just knows that to reach your final destination, you first need to get to Los Angeles. Once you're in Los Angeles, the local GPS, which is VPC N2's route table, will guide you to the local road, the VPN tunnel. This is exactly how VPC routing works with custom route import and export. VPC N1's route table says, to reach 10.10.0.0/16, send traffic to VPC N2 via the peering connection, which is VPC N1 to VPC N2. Once the traffic reaches VPC N2, VPC N2's route table takes over and says, to reach 10.10.0.0/16, send traffic through the VPN tunnel. This abstraction is powerful because it allows VPC N1 to reach the on-premises network without needing to know the implementation details of how VPC N2 connects to it. If VPC N2 later changes from a VPN to Cloud Interconnect, VPC N1's routing doesn't need to change. Best practices and real-world applications. Understanding custom route import/export is crucial for designing enterprise-grade Google Cloud architectures. This feature enables several important patterns that you'll encounter in production environments. The hub and spoke topology is one of the most common uses. You designate one VPC, the hub, to host all external connectivity, such as VPN, interconnect, or internet gateways. Other VPCs, the spokes, peer with the hub and import its routes. This centralizes connectivity management and reduces costs by avoiding duplicate VPN or interconnect connections. Security is another consideration. By centralizing external connectivity, you can implement consistent security policies, firewall rules, and monitoring in one place. The hub VPC becomes your security perimeter, making it easier to audit and control external access. However, there are limitations to be aware of. Transitive peering is not supported. For example, if VPC-A peers with VPC-B, and VPC-B peers with VPC-C, VPC-A cannot reach VPC-C through VPC-B. Each peering relationship is independent. Also, be mindful of route limits and potential routing loops when designing complex topologies. For the exam, remember these key points. Custom route import/export must be explicitly enabled. It allows sharing of all custom routes, not just subnets, and the next hop for imported routes is always the peering connection from the importing VPC's perspective. These concepts are frequently tested because they're fundamental to hybrid and multi-VPC architectures. Thank you for your attendance. Please consider subscribing to the channel.